Hello dear students, welcome to the foundation course for PU1 Science. Myself Arun Chidling from Department of Physics will continue with the lecture on calculus. So as in my previous class, as I had told you that calculus has two branches. Those two major branches are differentiation and integration. In the previous video lecture, we had studied differentiation, and now in today's video lecture, we are going to study integration. So today's topic is integration. So let's begin with it. Integration is opposite of differentiation. In terms of mathematics, we call it as antiderivative. I mean to say, the reverse procedure of differentiation will be integration. So let us try to use this concept to move ahead with integration. I hope you have seen this symbol. This symbol is called as sigma, which is used in summation. So it is used to find sum of finite numbers. Now assume that you have infinite numbers, unending numbers, then how will you do it? So there comes integration for rescue. So we try to use integration to find sum of infinite numbers. So it is represented by this symbol. The symbol is elongated S and we call it to be integral or integration. Let's move ahead and try to understand what exactly integration does. Integration of a function is defined as the area between the function and the x-axis. What do I mean by this? Let us try to take a function. So if we integrate the function, then we get the area between the function, I mean to say the curve, and the x-axis. So the shaded region here. So I've taken the limits for them. The limit is between x1 and x2. Between this I'm trying to find the area. So integration gives me the area here. Now, to get this area, I will try to make things bit simple so that integration becomes easy, right? So let me try to divide this area into some segments. The reason to divide this area into segment is I cannot directly find the area of the segment or this region. The reason is it is not a regular geometrical shape. Neither it is a trapezium nor it is a somewhat a rectangle. So I'll try to divide this area into some rectangles. Here these are rectangles but not exactly in a proper manner, right? At the top I don't have a exactly straight line over the upper end. So if I make the breadth small, then I'll be able to make proper rectangles, and if I go on adding such rectangles, then I'll get the area of this region, isn't it? So my intention is trying to make these rectangles as small as possible. So let us try to take one small portion from here. So I've taken a small portion. I'll try to find the area of this one, right? So let us write area of this shaded region will be written as dA. I am trying to take a small region. The total area will be A. This a small region will be dA. dA is equal to length into breadth. I am a bit wrong, but let us try to consider it to be a rectangle itself. Okay, so I'll try to write length as y and breadth as dx. Let me substitute here. So this will be length and breadth. Now if I want to find out total area between x1 and x2 under the curve, then I need to do is summation of dA. I need to add such areas. Okay, these areas I have to go on adding from here till here. right? But here if I try to do that, I have a small problem, that is I'll not be able to compute the values very precisely. That is, I'll be losing such small piece of areas. So what shall we do if I should not lose such small piece of areas? Then I need to do is I have to make dA very small. That means I need to make this rectangle with a very small area. It means to make dA very small, I need to focus on this side of the equation. Here I cannot change y, but I can change dx. It means I'll try to make dx very small such that this rectangle appears to be like a line. Okay, that's what my intention is here. That is to make dA tend to 0. I means dA has to become very small. That means dx also has to become very small. So this now will be replaced with integration dA. Now let me try to substitute the value of dA. So we know dA can be written as y dx, and the area has to be found out between x1 and x2. So if I try to solve this, I'll get the area. This area I'm going to get if I solve it. So here x1 is the lower limit, x2 is the upper limit, and I'll be getting the value between these two limits itself, right? Moving ahead, now what if the limits are not given? Then I'll be able to write it in this manner without the limits. That means there is no boundary on this side, it extends till infinity on this side and infinity over this side. So there is no limit. I have to find it to this end, to that end. There is no limit for it. Now these two type of integrals are called with a different name. This one is called definite integral since it has two limits or boundaries, and this is called indefinite integral since it is not having any limits. Moving ahead, let us try to write down some of the standard formulas for indefinite integrals. So without limits. So first one would be integration x raised to n dx. Here in the place of y we have x raised to n. So y equals to x raised to n. So in the place of y I have written x raised to n. So this integration will give out me the value to be x raised to n plus 1 divided by n plus 1 plus c. Here c is integration constant. Since this is indefinite integral, we need to add integration constant. So next will be integration 1 by x dx equals to log x plus c. Again c is integration constant. Next, integration of e to the power x dx equals to e to the power x plus c. Further, integration of sin x dx will be minus cos x plus c. Lastly, integration of cos x dx will be equal to sin x plus c, and at every point c is integration constant. Now let us move ahead and try to understand one problem on this one. Let us try to take a curve y equals to x square, and let's find its area, but between the limit x1 equals to 1 and x2 equals to 2, right? So I'll use the formula area equals to, that is integration value equals to integration x1 to x2 y dx. Now here I shall substitute the values. So before I substitute, let me first of all understand how will be the curve of this equation or this function. So the curve of this function is here, the red line, that is y equals to x square, and the integration what I'm trying to do, this area is here, from here till here, the yellow region shows that, and the lower limit is 1 and the upper limit is 2. Let me try to substitute their values to get the integration or the area under the curve between 1 and 2. So I have put the value of y here as x square, and we have the value of x2 and further value of x1 here. Next, we shall integrate it using this formula. In this formula, I have integration as it is x as well as here, and n has become 2. So if I put the value of 2 in the place of n on the other side, I'll get the integration values. Since this is definite integral, I don't get plus c over here. So because it is having limits, I don't have to put plus c. Right. Moving ahead, let us put the values. That is, in the place of n, I have put 2. That will be x raised to 2 plus 1 divided by 2 plus 1. So this comes out to be with the limits. So I have to put the limits also. So this integration value is bounded between the limits 1 to 2. Moving ahead, let us simplify it. So once it is simplified, I get the value x to the power 3 divided by 3 bounded between the limits 2 and 1. Further, I need to do is plug in the limits in the place of x. That is, I need to put the value of 1 and 2 in the place of x here. And then I need to do is subtract lower limit from the upper limit. Means I have to put 1 and 2 values here, and then further I need to substitute their values by trying to take upper limit minus lower limit. So upper limit is substituted in the place of x. It comes out to be 2 minus putting the lower limit in the place of x, then trying to write it. Further, simplifying ahead, we would get this value. In the place of 2, you will get 8, 1 would come out to be 1 itself. Further, you will get 7 by 3 units. So the area between that region, which I had shown with the yellow shade, will be 7 by 3 units. Moving ahead, let us try to understand why do we need integration in physics. Integration is necessary in physics to calculate displacement from velocity. If velocity is given, we can find out displacement. As I have already told you that in the previous video lecture, we can calculate velocity from displacement, and this video I am telling you we can calculate displacement from velocity. That means you can clearly get to know that integration is antiderivative. That means it is a reverse procedure of differentiation. So similarly, we can also find velocity from acceleration, right? And also in some cases, when force is not constant, we need integration to get the work done, right? Moving ahead, it is majorly used to study summation of infinitely many small factors, right? So this is the use of integration in physics, and there are many more which you'll be studying as you go on with the course. Thank you, dear students, and see you in the next video lecture.